Okay, in today's lesson, we are going to move from the ground floor of 3D vectors to the full stage. We've flown along lines, we've explored direction vectors, parametric forms, and intersections of vectors, but now it's time for the big one, the plane. So what is a plane? Well, you can think of it as an infinite sheet of paper. It's perfectly flat, it doesn't have any edges, and imagine it extending forever. You can think of it as extending forever in this direction and forever in this direction. But what we have to remember is that it has an infinitely wide, it's infinitely long, but it's flat. It has no depth. Okay, so infinitely wide, infinitely long, it has no depth. Unlike a line, a plane actually needs more than just one direction to be able to describe it. It needs two. Why? Because a line moves in one dimension and a plane actually moves in two. If we were to take a look at this image of a plane, we can see that it actually is it's taking 3D coordinates and making a flat surface. So today, you're going to learn how to describe that plane, an infinite flat surface that stretches endlessly in every direction within space. Another way to think of it is a perfectly smooth tablecloth or a sheet of paper that goes on forever. And that's what we're working with. So how do we define a plane in math? Well, Google Dictionary defines a plane as a flat surface on which a straight line joining any 2 points on it will wholly lie. So what does that mean? If I've got 2 points on here and I draw a line between them, it's going to lie on that plane. Now, the calculus textbook will tend to define it as planes are flat surfaces that extend infinitely in all directions. So forever and ever in all directions. In order for us to define it mathematically, though, we need a couple of things. We need at least 1 point and we need a direction vector. So think of it as a line only moves in one direction, a plane moves in two. So what do we need? Well, we are going to need a point somewhere on that plane and 2 direction vectors that lie within it. So why does all of this matter? Well, because this is how we describe 3D surfaces mathematically in architecture, computer graphics, physics simulations, and even flight paths. Planes just aren't theoretical. They're everywhere in applied math. So today we're going to build these equations ourselves. We're going to understand how they work, how to interpret them, and how to tell when 2 planes are the same or just parallel strangers. So let's get started. Okay, so to determine the equation of a plane, we need to know 2 non-collinear vectors that are parallel to the same plane and a point. And we can determine this information in a few different ways. I'm not going to go through all of these in depth, but there are 4 different ways that we really could think about it. We could have a line and a point laying on the plane. And we could see that this is my one direction vector, and I could put a point anywhere on here and draw another direction vector from a point on that line to our other point. Same thing here. If I have 3 non-collinear points, just means 3 points that aren't parallel to each other that lay on the plane, I could get a direction vector from AB. I could also get a direction vector from AC, and then I could use that plus 1 other point to figure out the equation for this plane. We also could do it with 2 intersecting lines, which is this one, or with 2 parallel and non-coincident lines. So 2 parallel lines that lay on the plane, but aren't overlapping over top of each other. Okay, so let's get some definitions around here and let's start looking at this because it's going to look familiar. It's really not all that different than the vector equation of a line, vector equation of just a line. So let's take a look at what we've got here. So the vector equation of a plane, that's this one here, is the sum of 3 different vectors. We have our position vector, x naught, y naught, z naught. plus scalar multiples of two other direction vectors. And that's this t is the scalar multiple times ABC, and we have s is a scalar multiple times vector DEF. Planes are always in 3 space, so our resultant will have x, y, and z components, and so will our position and our 2 direction vectors. So if we wanted to think about what all of this means, we could say, remember that r is our position vector, and r is really equal to x, y, z. So this is just a position vector for any point on a plane. And remember, it starts from the origin. So it's going to be the position vector that tells us how far away the plane is from that origin. Then we have, this right here. Then we have r naught, and r naught is equal to x naught, y naught, z naught. That's just the position vector for a known point on the plane. So we could, from the origin to some known point on the plane, those are the coordinates for that. Then we have this d and this e. This is d, one direction vector. This is e, the second direction vector. And they're non-parallel direction vectors that are parallel to the plane, but not to each other. And t and s are just the scalar multiples. So if we know the vector equation, then I think we can see, just like when we had the vector equation of a line, if we have the vector equation of a plane, we can go ahead and easily break it into its parametric equation. So we could have an equation for x, y, and z components of each part of this vector equation. So the x component, this x component here, this is the parametric. So the x component of the parametric vector is just the x component of the position vector, this x naught, I'm going to change colors, this x naught, and then it's going to be plus a scalar multiple of the x component of direction vector number 1, so we have t times a, plus a scalar multiple of the x component of direction vector 2, this is s times direction vector e. So it's the same, and it's the same for all 3 components, x, y, and z. We have x naught plus ta plus sd, y would be equal to y naught plus tb plus se, and our z component would be equal to z naught plus tc plus sf. We're just taking the x, y, and z components of each one of those direction vectors, d and e, and multiplying them by that scalar multiple. So I want you to think about this. Is there only one vector equation for each plane? What do we think? Well, no, there are infinitely many equations for the same plane. You could pick any point on the plane to use as your reference point. If the plane has infinitely many points, you have infinitely many choices for your r naught, for that position vector. There are also infinitely many pairs of direction vectors that lie along that plane. As long as they're not parallel, so not scalar multiples, they will span the same plane. Even changing their magnitude or direction slightly without making them parallel gives you a new but valid pair. The geometry of the plane doesn't change, just the way you describe it does. So let's pop over to GeoGebra and just take a look at what this looks like in 3 dimensions. Okay, so here is our plane in 3 dimensions. I've gone ahead and I've put 3 points on here. That's how I've created the plane, because remember I said to you, we could, if we have 3 points, we can create a plane. And if we slide it around, we can see that this is what this actually looks like in 3 dimensions. It would go on forever up this way, forever out in both directions, but it's never going to get any deeper. It's really just going to be flat. We can see our points through it. So that's what that looks like. So let's go ahead and let's put these equations to use and start doing an example. Okay, so let's look at an example. We want to determine the vector and parametric equations of the plane that contains a point, 5, -1, 7, and the line, xyz, is equal to the position vector, 2, 1, 9, and the direction vector, t times 1, 0, 2. Okay, so how are we going to do this? Well, what do we know? That's always the first thing. So we know we have a point, and let's call this point P, on the line at 5 negative, or on the plane at 5, negative 1, 7. And we've been told it's on the plane. We also know that we have a line that's on the plane. And the line on the plane is xy, is represented by the vector of equation xyz with a position of 219, or a point vector of 219, plus our direction vector of 1, 0, 2 with some scalar multiple. And we know that on this line, if it's on the plane, any scalar multiple of that direction vector will give us another point on that plane. So how do we tackle this? How are we turning this into our vector equation of the plane? Well, the very first thing that we need to do in step 1 is to find a vector on the plane using a given point and a point on the line. So we are going to find a vector on the plane using what we know. We're going to using the given point, a given point, and a point on the line. Well, we have both of those things. Okay, so we're going to say, actually, I'm going to change back to other color here. And a point on the line. Okay, here we go. So we're going to let A be a point on the line. So we know that we have a point at 219. It's going to be a point on the line. So we can determine a vector AP from our point A. And remember, we have point P that we already knew was on the plane. So we can get AP by doing our x2 minus x1, y2 minus y1, z2 minus z1. So we have 5 minus 2 for our x value. We have negative 1 minus 1 for our y value. And we have 7 minus 9 for our z value. That gives us a vector that has a point at 3, negative 2, negative 2. Okay, so now we've found a vector on the plane using a given point. So now the next thing that we need to do, step number 2 here, is to find a second vector on the plane. And to do that, we're going to use the direction vector that we already have. So find a second vector. To find a second vector on the plane. And to do that, we're going to use the direction vector of the line. Okay, so my direction vector of my line, just from right here, is 1, 0, 2. So I've got a vector on the plane, that's AP. I now have my direction vector. So now we're going to go ahead and we're going to put it together and we're going to write the vector equation of the plane. So we're going to write the equation, write the vector equation of the plane using what we know. We are going to use the fact that we have a point A that's at 2, 1, 9. That's the point on the line. We have vectors AP, which was the vector that we created, and we have vector D, the direction vector. So let's put it together. So we will get x, y, z. So vector of the plane is equal to my point, 219, that's my position vector, plus, now remember, this is where I need those two direction vectors because it's a plane. I need to know the two directions in order to determine where the plane is. So we have a scalar multiple times 3, -2, -2, plus a scalar multiple times 1, 0, 2. And that is our vector equation. Once we have our vector equation, it's pretty simple to go ahead and create the parametric equation, because remember, we're just breaking down the x, y, and z. So we would have x is equal to 2 plus 3t plus s. So 2 plus 3t plus s. Y will be equal to 1 minus 2t, and this is s times 0, so nothing there. And z will be equal to 9 minus 2t plus 2s. So there's our parametric equation. There's our vector equation. So the next thing we want to think about is how many normals can each plane have? So remember, a normal is just perpendicular to a line. That's how we've always thought about it, is that the normal is just perpendicular to the line. But each plane, if we think about it, could have an infinite number of normal vectors. So while a plane has one specific direction perpendicular to it, any vector that's a scalar multiple of that direction is also a valid normal vector. So how could we find the normal to a plane? Well, remember, it's perpendicular. So we can say that the normal will be equal to the cross product between the two direction vectors. So let's take a look and let's see what that looks like. Let's jump right into an example. Okay, so we want to determine whether the following planes are the same. So if they have the same normal, then they are either going to be parallel or coincident. Those are our two choices. So the very first thing that we're going to do is find the normal for each one of those planes. And remember, I said on the last slide, we can find the normal. So you can get the normal by taking the cross product of the two direction vectors. So we can take the cross product of direction vector D crossed with the cross product of direction vector E. Here's D, here's E. I have two planes. I'm going to compare them to see if the normals are the same. So let's go ahead for plane number 1. Let's go ahead and find the normal. So we know that we have direction vectors. My D is equal to -1, 5, and 2, and E is equal to 2, 4, 2, and we're going to cross them. So N1 will be equal to D crossed by E, which is equal to -1, 5, 2, crossed with 2, 4, 2. Now remember from the last unit, if I'm taking the cross product of something, I'm starting at my second value, my y value, and I'm just writing them out. 5, 2, -1, back to the 5. Same thing for this one. I'm starting at 4, 2, 2, 4, and I can take the cross product of that. So that's going to be 5 times 2, 5 times 2 minus 2 times 4. 2 times 4, 2 times 2 minus -1 times 2. And then we have -1 times 4 minus 5 times 2. My dog has decided to chase the cat, if that's what you're hearing in the background. I'm not sure if you guys can hear it or not. So that equals 10 minus 8. Five times 2, fix where I just, oh my goodness, I'm making it worse. Okay, hold on. Let's fix this up a little bit so it's not looking quite so scattered. So we have 5 times 2 minus 2 times 4. And then we had 2 times 2 minus -1 times 2. Okay, here we go. Now that I've got that back there. So this gives us 10 minus 8. It gives us 4 plus 2. And it gives us -4 minus 10. So my normal for plane number 1 is going to be 2, 6, negative 14. Okay, so now if they're, I'm going to find the normal for the second one, and then we're going to see if they are actually parallel to each other. Okay, so now where am I going to put that? Because I took up a lot of room. Okay, so I've gone ahead and just done the cross product for plane number 2. That was simply just my direction, my 2 direction vectors from plane 2, D and E, cross product them together to get a normal of 49, 147, negative 43. Now, we need to check to see if n1 is a scalar multiple of n2. So really we want to know, I'm going to make this bigger, is n1 equal to some scalar multiple of n2? And just because n2 is bigger, I'm actually going to change that up a little bit. And we're going to say, is n2 equal to some scalar multiple of n1, because the direction of that doesn't matter. So we could set up a system of equations to do that, just relating n1 to n2, and just see if those k values are the same. So we could say 49 should be equal to 2k. So k would be equal to 49 over 2. That's our x value. Then we would say 147 would be equal to 6k. So k would be equal to 147 over 6. And that does indeed reduce to 49 over 2. And then for the final one, we would have negative 343, that's this value here, is equal to negative 14k. And k here will be equal to negative 343 over negative 14, and that also reduces to 49 over 2. So since all of the values of k are the same, the normal vectors must be parallel, but they could also be coincident. So they could be parallel, meaning they never meet, or they could be coincident, meaning that they are the same. Remember, coincident means the same. So how could we figure that out? Well, we can take 2 points and create a vector AB, very similar to what we did on the last question, and cross AB with any of the other direction vectors. If it's on the plane, you'll get the same normal as n1 and n2. So let's give that a try. So we have from plane 1, we know that we have a point, let's call it A, of 0, 3, 2. That is just this here, 0, 3, 2. So we have 0, 3, 2. And then from plane 2, I'm going to do the same thing. I'm going to call this point B, and we're going to say negative 2, 6, 3. And again, I just got that from right here, negative 2, 6, 3. They are 2 points. Okay, so now we're going to cross those. We're going to create a vector, and then we're going to cross that vector with any of the other direction vectors. So let's get AB. Again, x2 minus x1. So we have negative 2 minus 0. We have 6 minus 3. And we have 3 minus 2. That gives me a direction vector, gives me vector AB of negative 2, 3, and 1. So now if I cross this, if I cross AB with either one of the direction vectors, and I'm going to choose to use, so AB was negative 2, 3, 1, and I'm going to choose to cross that with just one of the direction vectors. I'm just going to use negative 1, 5, 2 from plane 1. So we're going to cross that with negative 1, 5, 2. Okay, so what do we get when we cross that? So we have 3, 1, negative 2, 3. We have negative 1, 5, 2, negative 1. So we get 3 times 2. minus 1 times negative 1. We get 1 times 2 minus negative 2 times 5. And we get negative 2 times negative 1 minus 3 times 2. So let's see what we get. We get 6 minus, oops, I made a mistake. Okay, take 2 on this one. I realized what I did. When I went to do the cross product, I had my second vector in there incorrectly. So here we go with this. So we have 3 times 2 minus 5 times 1. We have 1 times negative 1 minus negative 2 times 2. And we have negative 2 times 5 minus 3 times negative 1. Okay, let's do a little bit of math on there. I think I've got it right this time. So now we have 6 minus 5. We have negative 1 plus 4. And we have negative 10 plus 3. So this gives us a direction vector for this. We'll call it N3, for lack of a better thing to call it, of 1, 3, negative 7. So I think we can see that this is actually a scalar multiple of both of these normal vectors. Therefore, the planes are the same. So that means they are coincident. So a coincident plane will always have equal or scalar multiple vectors. But in this case, the two planes lie exactly on top of each other. Every point on one plane is also on the other. They're just two ways of describing the same plane. So what does that look like? Well, let's go take a look at it. So here's plane 1. That's the blue one. And if I add plane 2 into there, we can see that it's going directly on top of it. We don't have any separation there whatsoever. So that's showing me that they are coincident. Now, what if they were parallel? So what if they had equal or scalar multiple normal vectors, but they never intersected? Well, they end up like two flat sheets that never touch. They do not have the same plane. So if we wanted to take a look at what that looked like, all that I've done is I've changed the position vector. So this point, 0, 0, 0, is no longer on plane 2, and that's what makes them different. They actually are very distinct, like two separate sheets of paper, and they are never going to meet. Okay, let's pop back over to here. There we go. So that is it for today. That's a lot of new information and new ideas to take in. There are no homework questions for today. So I want you to make sure that you're going back and doing all of the practice questions, getting caught up on anything you haven't done yet. And there will be lots of homework questions coming for the next lesson. So don't worry if you're feeling like you want more homework to do. As always, if you have any questions, feel free to send me an email.